Okay, so this is our group project for A4791, namely the final Laminator project. Our group is consisted of Arvin, Ajmani, Jared Merenuk, myself, Mikkel Ormstrup, and Hannah Fischer. So our project specifically was the second portion, which had a high modulus carbon fiber as our fixed parameter, leading to our design variables being our type of matrix, our total type of laminate, our angle ply, fiber volume percentages, and as a result, our three driving parameters were thickness, cost, and weight. And so before we began, we all individually created our own prototypes. And from those four prototype laminates, we discussed and debated, and we converged on one general first order solution. This was our initial design. And then given our input loads, we then ran that through the laminator dozens of times. Our main failure criteria was the one that the laminator software uses, which is our conservative first ply failure. And if the laminate failed, then we would go back, reconfigure it, change up the layout, change up our specific parameters. This is going to go into more detail later on. And then just iterate until we got a good solution. Once we got a good solution, we'd iterate that and optimize it for our design variables. And then once we were satisfied, we were finished with our final laminate. And so should our laminate failed, we had our reconfiguration loop, and that was essentially broken down into materials and how we stacked those materials. So our materials, one half of it was essentially fixed. That was our high modulus carbon fiber. We had some options there, but generally there was a little wiggle room there. Aside from that, we had our matrix, and we started off with an epoxy because that's a pretty common solution, is to have a high carbon fiber or high modulus carbon fiber with an epoxy solution. Given these material makeups, the majority of our time was spent fiddling with our stacking. So that was how we ordered our layers, how we avoided clustering, how we got a balanced or symmetric laminate. Aside from that, another consideration was our gradation in angle plies. So we tried to avoid like something extreme like 0 to 90, and generally we would put in like a 45 to keep those gradations and interlaminar forces minimal. Another general rule of thumb we employed was if we had a certain amount of forces in the X direction and a certain amount of forces in the Y direction, we'd give us appropriate angle plies given those conditions. So if our force in the X direction was twice as big as that in the Y direction, we'd have twice as many axial ply laminas than in the transverse. And so if our loop was successful, we then would optimize our three main parameters, which are given in the project prompt. Those were weight, which is correlated to density, our cost, and thickness. And we just iterated dozens of times until we got a good solution we thought was as best as we could go. And so those were our three driver variables, thickness, weight, and cost. And considering they're all essentially intertwined, we have our thickness, which is, if we have a thicker lamina, it's going to weigh more. It's going to have more material, so it's going to cost more. As a general, like compared to other materials, carbon fiber epoxy composites are significantly lighter, and they're stronger than their alternatives, mainly like steel, for example. So weight wasn't a major concern. Whatever solution we got was still going to be a lot lighter than the alternative. And so given that, our main driving variable was then resolved to be cost. And that's because carbon fiber is just significantly more expensive than its alternative. Carbon fiber is about $25 a pound, whereas steel is cents. It's about 36 cents per pound. And so given all of our consideration and how we worked it out, we had our final solution be a simple 090 laminate, so 2 layers, and the total thickness wound up being only 1.5 millimeters. We used a GY70 as our carbon fiber, and the epoxy is not listed here, but it was, what was it, like 934 epoxy. So given it was a super thin 12 inch by 5 inch by 1.5 millimeter laminate, the weight wound up being pretty low. It was only about 100 grams, and so there wasn't a whole lot of material, and the total cost wound up being, this is purely based on rule of mixtures and the material alone. Manufacturing and production like difficulties aren't at all considered here. It's a very first order estimate, and as such, our total cost wound up only being about $5.48 per spar cap.